first one is Bridger Corkill, engineer for the Nebraska Department of Water, Energy, and Environment. And with that, I will hand over to Bridger.
Thank you, Arindam. I appreciate the introduction there. Let me unfold my notes here. Can't do this without them, but I really appreciate the opportunity to be here with you all today and share some updates we've made to a model developed for the Department of Water, Energy, and Environment. We used to be NDEE. In 4 years, I've gotten to work for 2 agencies without changing jobs, so we'll see how many we are at by the end. We don't have very much time together, so I'm just going to jump right into this and start talking to you about our modeling. So today we're going to go on a journey from the map that you're seeing on the left to the one that you're seeing on the right. But before we can really get into the mapping and the modeling, I kind of want to tell you how we got here. Last year, the Nebraska Department of Environment and Energy at the time, we were tasked with doing a statewide nitrate study focusing on nitrate in drinking water. And as a part of that nitrate study, we also developed a predictive model to try and identify areas where private domestic wells were at higher risk of exceeding the nitrate standard of 10 milligrams per liter. Up top, I will emphasize, we understand that model results are not field data. The best way to understand your water quality is to test your well. But with that caveat in mind, our objective was to develop a model to supplement a GIS tool that helps private domestic well owners understand their water quality and just kind of broadly where their water is coming from. And to accomplish that objective, what we did is developed a model in R to make predictions to a set of wells across the state. And then we used that modeling to generalize the predictions into a statewide product. And we worked with some project partners and experts to try and decide how we can most effectively use it. So even though we're going to cheat and use machine learning, we still have to have a good physical conceptual model of our system before we start modeling. And this up here is a diagram of the nitrogen cycle. I'm not going to get too into the weeds in it today, but for our purposes, we're really just concerned with when there's excess nitrogen in the system. So nitrogen, very important for plants to grow, but when we have too much nitrogen applied at the surface in Nebraska, some of that can leach down into groundwater where it becomes nitrate. Elevated nitrates in drinking water are a public health issue, and so that's really why we care about this here in the state. But beyond just our municipalities, quite a few people in the state rely on private domestic wells, and as someone mentioned earlier, since they're responsible for their own water quality, it was really important to us to try and develop a tool that could help explain some of these things to them. We're just going to talk about the modeling today. So once we got our conceptual model in mind, we started gathering data related to our process to try and identify relevant conditions and hydrogeologic factors to include. So those are things like soil infiltration, soil type, pH. We also looked at things like well construction details. So how deep is the well? Where is it screened? Is there a surface seal? And we looked at potential sources of nitrogen out in the environment. And this was kind of broken into 2 categories. So we looked at non-point sources, and mostly we captured these data with land use. So what kinds of crops are growing in the area? What is the land use surrounding the well? And we also looked at point sources. And I want to emphasize that our point source data set is limited to facilities that we regulate. So we permit animal feed operations and certain types of chemical storage. So potential precursors to nitrate in groundwater were included in our modeling if they have to receive a permit. I'm going to try and cover this method in like 3 slides. So if anyone wants to hear about the actual math that goes into it, please catch me afterwards. But essentially what we did is we used a method called boosted regression trees, which is a type of machine learning algorithm to develop this model. And so we took a set of training data, which are wells from the Nebraska Groundwater Clearinghouse and a lot of different hydrogeologic factors, and we used it to develop a model. Then we took another set of wells data that are testing data that we didn't include to train the model, and we used that to evaluate the model. How well is it going to generalize? What are the kind of performance statistics that we're getting? And this is kind of an iterative process so that hopefully we're improving things over time. Now, to get from a model at the well level to a model at the state level, which is something that we need to query for our GIS tool, we needed to generalize the modeling. And so to accomplish that, we essentially took the same stack of variables that we used to predict at each well, And we assigned all of those to a grid across the state of Nebraska. And here with our modeling today, we're going to be looking at 3 different nitrate threshold concentrations. And we're trying to identify areas where private domestic wells are likely to exceed those thresholds or fall below them. 10 milligrams per liter is the regulatory limit, and so it's something that we want to identify those areas. 5 milligrams per liter is EPA designates that an elevated level, and 3 milligrams per liter is what we consider the upper end of the transitional background range. So if it's above 3 milligrams per liter, we can be pretty certain that anthropogenic sources are causing the nitrate in the alluvial system. And that's kind of how we use the model to identify areas where private domestic wells are likely to exceed those thresholds. We combined all these predictions into one map for our GIS tool. So we look downwards with a query from the most important down to try and to report back to the user essentially what we think is likely for their area. So that is how we used this method to develop this map. The biggest change that we're looking at here today is in the types of input variables that we had available to us. So in the original version of our map product, a lot of the Surgo soils variables were not available at the time. It turns out that if you're not a soil scientist, it's very complicated to compile statewide soils data in a way that's defensible. Thankfully, the state soil scientists came to our rescue, but we didn't get the data in time for our initial publication. So we made do with a couple of other factors to try and capture these soils factors indirectly. With the product we're looking at today, we've removed those indirect variables and instead included all of those factors from the soils database that we initially wanted to include. This was very exciting to me. These are very similar to variables lists used by USGS scientists who have looked at nitrate in private domestic wells in like the Central Valley in California, as well as in Iowa. And I joke around the office that if I had access to supercomputer time, I would have just directly copied their homework. That being said, I think even with just my office computer, we do pretty well. Before we look at the map product, I want to show you what it looks like at the well level. So this is before we generalize the model, we map it to try and identify areas where things are performing how we wouldn't expect them to, or if there are geographic patterns in like poor model performance. So generally you can see that the model performs best in areas where we have a lot of samples and in areas generally where we're in like river valleys and we're dealing with relatively shallow alluvial aquifer systems. And then in areas where the connection between groundwater and the surface conditions are much further apart, that is where we tend to struggle more, which kind of makes sense for a groundwater model. The other thing that we wanted to do is see how well this map would perform actually in our GIS tool. And so we wanted to compare this to a set of private domestic well samples that we collected as a part of our nitrate study. There's a lot of caveats with this comparison, but our goal here with the model is to provide a ballpark estimate of where those wells are likely to follow and to help educate those private domestic well owners. I will caveat this. The well location data here is geocoded from addresses that were reported by the owners when they collected these samples. And while I've done my best to remove PO boxes, I do think that I can probably extract these data from the clearinghouse and shape up this comparison a little bit. But the other thing I actually want to highlight here is that we didn't collect data on which well owners were treating during our free sampling effort. But from the data we got, it was pretty obvious to us that some people were. A lot of people wanted to test their RO systems, so they requested a sample that they took before the system and one they took after. So in those cases, it was really easy to just take the higher of the 2 samples to get to groundwater, but our staff fielded about 2,500 calls when we were collecting all of these samples, and based on those conversations, somewhere between 10 and 30% of people probably have a treatment system here that's definitely impacting those numbers. One exciting thing that we get out of this method, I think, and one of the fun things about these machine learning methods is we can use things like variable influence plots to find out what is going into our prediction. But more importantly, we can see if this squares with our physical understanding of the process. So here we're looking at a measure called variable influence. And this is basically just a relative value for how much better each one of the factors makes the model predictions. The two most influential variables that we're seeing here are the percentage of sandy soils around the well in yellow and the well depth there in that kind of pink magenta color. One thing I'll emphasize about variable influence is this is not quite the same as a regression coefficient. So you wouldn't say sand explains 7% of the variance in the data. It's just a measure of like how much better each one of these variables makes the model. The other thing to note, if you go online and interpret these data later, for variables that we don't have complete coverage for, so like in Nebraska, we record well construction details when the wells are built and registered. And so things like our pumping water levels or our static water levels may not be recorded at all wells. And those levels are going to come from different periods of time, depending on where the well was built. Whereas when we're looking at the percentage of sandy soils, we have 100% coverage across the whole state. And I'll talk a little bit about why that matters in a bit. The other interesting thing I think we get out of these methods to help us evaluate how the model is doing are these things called partial dependence plots. And so these are just basically looking at how does the likelihood of exceeding those nitrate threshold values change for each one of our individual predictor variables. It's not a perfect relationship, you wouldn't want to try and plot from here, but this gives us an idea of like, is the relationship positive or negative, and what kind of range of variables are going to impact that value. So I put a dotted line along the 0 axis on the y-axis. So things above the red line are more likely to exceed the threshold. Things below are less likely. I will highlight well depth on this screen. Let's see. This does show pretty much exactly what we would expect. As your well gets deeper, the surface conditions are generally less relevant. Your relative risk of seeing elevated nitrate level goes down. Now, this isn't universally true because, of course, an improperly constructed well itself can be a conduit for contamination. But the fact that this trend exists in these plots suggests that we're collecting or we're capturing some of that physical relationship we'd like to capture. The other one I wanted to highlight from this set is the soil organic matter. I thought this one was just kind of heartening. The results here suggest that as we build up our soil organic matter, our relative risk of nitrate contamination goes down. This is not a method that can prove causation, but there have been a lot of studies out there into the effective best management practices on nitrate in groundwater. And so it was encouraging to me that we see a similar relationship between organic matter and nitrate levels that have been reported in other studies. We're going to close out with looking at one final map here. We'll go back to the model results. And I want to talk a little bit about those spatial trends in data coverage again. So here, instead of looking at the concentrations, we're looking at the probability for one of the scenarios. It's the one for exceeding the MCL. And so this, you can see how that changes around the state. When we think about the variables that are the most influential on this model prediction, like for instance, well depth, I want to be very clear that we just don't have a well depth at every single one of these half-mile grid cells across the state of Nebraska. But we do have land use variables for all of them. So in areas where we have limited development, those land use variables are going to dominate the model prediction. And so I think this is probably leading to a little bit of an elevated risk in the sandhills, since there is very limited development, very sandy soils. It can only see the sandy soils part of the equation, and it kind of bumps that risk up. So yeah, just keep that in mind. If you're ever going out and interpreting these results or looking at them for some kind of a groundwater plan or anything like that, these results will be available on Nebraska Map in the same spot that the current nitrate model results are available. You'll be able to go there and search for nitrate. And this time, I promise, I've fixed the fields so that the field names all make sense. And ArcPro was cooperating with this time and didn't change them all when we uploaded them to Portal. That is really all I have for today. This is just a quick update. A lot of these changes were recommendations that we had made during the nitrate study, and so we're just excited to be able to share these new results.